In this chapter, we will discuss the changes associated with transferring energy from one system to another, often known as thermochemistry. Initially, we need to discuss some vocabulary. The first term that we need to be familiar with is the concept of thermochemistry. This is the study of the transfer of heat and from one system to another. So this is specific to the transfer of heat energy. The term thermodynamics is similar to the term thermochemistry, but is distinctly different in that it is the transfer of all kinds of energy between systems, not just heat. And then the term temperature. Temperature is a measure of the average internal kinetic energy of a system, and is often measured in a comparative way using thermometers. The term heat is the energy that is transferred from one system to another, usually a changing of the average internal kinetic energy. So therefore, if we have heat transfers, then we also are going to have temperature changes. We can define energy in terms of the ability to do work, and in chemistry, we are particularly interested in the so-called thermal energy or the energy of motion. And in this case, we can define this as the kinetic energy, which is equal to 1/2 mv squared. The units associated with energy are the joule, which is equivalent to the base SI units of a kilogram meter squared per second squared. The calorie, which is defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius, is equivalent to 4.184 joules. This is not the same as the so-called nutritional calorie, which is in fact 1,000 of these calories. And so a nutritional calorie is actually equal to a kilocalorie. In physics, we often talk about the changes in energy and the different types of energy. We can talk about potential energy, which in terms of the energy of position would be affected by gravity. And so if you see here an object such as a ball sitting on top of a wall, it has gravitational potential energy, because if it were to fall off of that wall, it would then begin to move, and that energy that was potential energy is now turned into the energy of motion, which is kinetic energy. Once it reaches the ground, that kinetic energy is transferred from the ball into the ground and is then released in some other form, usually in the form of frictional heat. So the energy that was stored in the ball on top of the wall is simply moving around and changing forms, but never created nor destroyed, and therefore we have the so-called law of conservation of energy. We can then also talk about the so-called first law of thermodynamics, which states that energy is always conserved throughout processes, and so we can never create nor destroy energy. We simply move it around when we do chemical reactions, and this energy can be put into bonds or change temperature of a system, or do various other types of work. So we can talk about the so-called internal energy, which is the energy that is stored within the particles on the atomic scale, and we can then state that the total energy of a system is the sum of three different types of energy. The E subscript K is the kinetic energy of the object moving. The EP is the potential energy. And then finally, we also have the internal energy. If you add those three things together, we can come up with the total energy of that particular system. So it turns out that we also can talk about any kind of changes in the internal energy, and this is given the symbol of the Greek letter delta and then E. So delta is always a final situation minus an initial, so to determine the change in energy, we would take the final energy that we have and subtract out the initial energy for the system. So, some additional terms. The first term we need to deal with here is the so-called thermal energy. This is energy that is associated with molecular motions, either translations or vibrations, and this is what's occurring on the atomic scale or the molecular level. So typically part of the internal energy. In addition to that, we have energy that is stored within chemical bonds, and this energy can be substantial. This is the energy that is holding various atoms together within a molecule. And then finally, we have the so-called radiant energy or radiation. This is what we discussed previously in terms of electromagnetic energy. At this point, we need to be able to define a system, and in this case, this system is a small portion of the universe that is being studied. And so in our picture here, we have an Erlenmeyer flask that has been filled with water, and then also contained within that are three compounds: hydrochloric acid, ammonia, and ammonium chloride. And so to define our system in this case, the system is defined as the chemical reaction that occurs when HCl reacts with ammonia and forms ammonium chloride. The surroundings are everything else. So the surroundings include the water, which is the solvent, and the flask and the air that is then surrounding that flask. So turns out then that symbolically in our reaction, the water, which is acting as our solvent, is part of our surroundings. So the universe is comprised, from a chemical point of view, the universe is comprised of two things: the system and the surroundings. And energy can be transferred between the system and the surroundings. At this point, we need to focus in a little bit more on what heat is. Heat is any energy that flows from a system that has a higher temperature to another system that might be at a lower temperature. And so heat is this energy that moves. And so when two systems are in contact with one another, we talk about the transfer of heat, not the transfer of cold. And so the transfer of heat then results in a temperature change. So as you see here, we have two objects both having some internal energy. The object on the left has a higher temperature than the cold water that is on the right, and therefore some of that internal kinetic energy is transferred to the colder water due to molecular collisions. And so by having the molecule that is moving faster collide with a molecule that is moving slower, some of that kinetic energy gets transferred over to the slower molecule, making it move faster and therefore increasing its temperature. So eventually the two systems will come to some sort of equilibrium, and therefore all the molecules within both systems will be moving on average at the same speed, and as a result we'll have the same average kinetic energy, which is what we define temperature to be. At this point, we need to define two terms, endothermic and exothermic. So if we have a particular system, which might be some reaction that is occurring in an aqueous solution, if the heat energy goes into that system from the surroundings, which might be the solvent or the air, then the heat is said to be endothermic, going in, and if the heat is coming out of the system, the so-called reaction, then that will be an exothermic process, and so that adds heat to the surroundings. In this particular situation, if the heat goes into the system, it must be coming out of the surroundings, and you would then notice that the temperature of the water would actually go down as a result of this endothermic process, and you would perceive that the aqueous solution would appear to be getting colder. So this is then, by definition, the so-called endothermic reaction. Conversely, if we have a system that is going to give off heat, that heat will go into the surroundings, causing the molecules, the water molecules, to move faster, and therefore the temperature would go up, and we would say that this is an exothermic process. So in this case, we say that the heat, which is given the symbol of Q, is negative, whereas an endothermic process, the value of Q would be positive. So we can summarize this in terms of the types of reactions and the observations that you might make. So if we have an endothermic type reaction, the surroundings, the water in the vessel appears to get colder. That's because the heat that was in the liquid water is going into the system, coming out of the water, and so energy is being added to the system, and we say that the sign of Q is positive. If it's an exothermic process, then the reaction vessel appears to be getting warmer because heat is coming out of the reaction, going into the water and the flask, and the motion of the molecules is faster, hence the temperature goes up, and so energy is being removed from the system, and we say that the sign of Q is negative.